Describing transformations of sinusoidal functions given graphs. Function notation. Sine function is written as f at x equals to a sine of open square bracket k multiplied by open round bracket x subtract d close round bracket close square bracket plus c. Cosine function is written similarly, replacing the sine part with cosine. When we analyze transformation of sinusoidal functions, it is easier if we identify a, k, d, and c in a certain order. Step 1. Identify the horizontal axis, the horizontal line that goes through the middle of the curve. This line helps us find the value of c. Step 2. Identify the amplitude, absolute value of a. We use absolute value because the amplitude is always positive. Step 3. Identify the length of one cycle, which is called the period, using the letter p. We then use p to calculate the value of k. The formula is k equals to 360 over p. We used 360 because there are 360 degrees in one circle. Step 4. Identify the phase shift from a base function, which gives us the sine of a and the value of d. Possible base functions that we can use are y equals to sine of x, y equals to negative sine of x, y equals to cosine of x, and y equals to negative cosine of x. This is the graph of the base function y equals to sine of x. This is the graph of y equals to negative sine of x. We can see that it is a reflection of y equals to sine of x along the x-axis and also along the y-axis. Y equals to cosine of x is a horizontal translation of y equals to sine of x, or a horizontal translation of y equals to negative sine of x. And lastly, y equals to negative of cosine of x is a reflection of cos of x in the x-axis. Example 8. Determine an equation of the following sinusoidal function. So here we have a graph, and we want to figure out what is the equation of this graph. So step 1, identify the horizontal axis, which is the horizontal line that goes through the middle of the curve. So first, we draw this line on the picture. So it goes through the middle of the graph. So we take the maximum point and the minimum point and find the middle of it. So the equation of the horizontal axis is y equals to 1, and therefore the value of c is 1. Step 2, we identify the amplitude, which is the absolute value of a. From the horizontal axis, we can draw a straight line or vertical line all the way to the maximum point, okay, making the line perpendicular to the horizontal axis. And we can see that the pink line is 2 units long. That's our absolute value of a. The maximum value is 2 units from the horizontal axis, so the absolute value of a, or the amplitude, is 2. We can also look at the minimum value. From the horizontal axis to the minimum value is also 2 units long. So therefore, the horizontal axis to the minimum value gives us an amplitude of 2. Step 3, Identify the length of one cycle or period of P. Using a positive sine function, we want to check the points that are on the horizontal axis. So, from the starting point to the end point of this one cycle, we can see that it is 120 units long. Okay, so P is 120, subtract 0, which is 120 units. So K is going to be 360 divided by P, which is 360 divided by 120, and we get 3. We can identify the period a little bit differently. Using a positive cosine function, we check the distance between the maximum points, because the cosine function starts from the maximum and finishes at the next maximum. So P equals to 150 units, subtracting 30 units, which is 120. When we calculate K, we get 3 again. If we use a negative sine function, we are going to check the points on the horizontal axis. This part of the sine function is negative, and we start from the negative side of the x-axis. When we calculate P, we have 60 subtracting negative 60, which gives us 120 again. So the value of K would still be 3. Lastly, we could use a negative cosine function, which means that we check the distance between the minimum points. So we draw from one minimum to the next minimum. P equals to 90, subtract negative 30. Once again, we have 120. So K will have a value of 3. It doesn't matter where we start, we will always get the same period. Now, we can actually use any part of the curve to identify one cycle. So let's look at the positive sine part. So in our example earlier, I used this part of the graph. However, I could have chosen this part, or this part to figure out the period. Similarly, I can use different parts of the curve to identify the positive cosine curve. I could start here, start here, start here, or start at somewhere else. For negative sine, I could start here, start here, start here, or somewhere else. For negative of cosine, I could start here, start here, start here, or somewhere else. We can also use the x-intercepts to identify the period. Here, I start from one x-intercept. I went up, went down, below the x-axis, and then came back up. And there are 3 x-intercepts involved in one cycle. I can go down first, come up, and then come back down. I am also using 3 x-intercepts. So in this case, I cannot just choose 2 x-intercepts for one cycle, because you can clearly see that you need 3 x-intercepts in total to make up for one complete pattern. Lastly, we can actually use any point as the starting point of a cycle. So I'm showing you an example where I start from pretty much the middle of nowhere, and then I need to be able to recognize the whole pattern until I stop. However, usually the values are difficult to read, so this method is not recommended. It's easier to focus on using sine or cosine or the negatives to figure out one period. Step 4. Identify the phase shift. Let's look at a positive sine function. Let's focus in one cycle and the starting point of that cycle. So compare this positive sine function with the base function y equals to sine of x. Both of them start from the y-axis. So that means there is no phase shift, and therefore d has a value of 0. If we use a positive cosine function, notice that I start from the maximum point and stop at the next maximum point. Comparing it with y equals to cosine of x, the image curve does not start from the y-axis anymore, so we do have a phase shift. So it is 30 units away from the y-axis. And so therefore, the phase shift is 30 units to the right, which means that d has a value of positive 30. Negative sine function. Focusing on just one cycle, comparing it with the base function y equals to negative sine of x, we have a phase shift of 60 units to the right. So d has a value of positive 60. Use a negative cosine function. Comparing the image function with the base function y equals to negative cosine of x, we would notice the starting point has a phase shift of 30 units away from the y-axis. So the phase shift is actually 30 units to the left, and d equals to negative 30. Let's put everything together. We have c equals to 1, amplitude is 2, k is 3. Using the positive sine function, d is 0, so when we substitute c, a, k, and d into y equals to a sine of k bracket x minus d, close all the brackets, and then plus c, we have y equals to 2 times sine of 3x plus 1. This is if we choose a positive sine function to explain the equation of this function. If we choose a positive cosine function, then d has a value of 30 instead of 0. And when we substitute, we would have y equals to 2 times cosine of bracket, 3 times x minus 30, close the bracket, and then close the square bracket, and then plus 1. If we choose a negative sine function, then d is 60, and we have y equals to negative 2 because it's the negative sine function, so a is negative now. Y equals to negative 2 times sine of 3 bracket x minus 60, close the brackets, and then plus 1. Lastly, if we have negative of the cosine function, then we have y equals to negative 2 cosine of 3 times bracket x plus 30, close all the brackets, and then plus 1. So there are 4 different ways to write this function. However, this is not the end. We write the degree symbol into the equation if it is not a word problem. For no phase shift, it's 0 degrees, but when we substitute d is 0 degrees, we don't really need to write it when we simplify, so we don't see the degree symbol. For the other three equations, we're supposed to have 60 degrees, 30 degrees, and negative 30 degrees if it is not a word problem. For word problems, the unit of x is often time in seconds, minutes, hours, days, months, or years. Note 2. We can write infinite number of equations to represent a sinusoidal function. Earlier, we worked out 4 equations that we can use. We can actually generate a lot more. How do we do that? We need the period, which is 120 degrees. Let's say I shift the function one cycle to the right. So then d is going to be 0 degrees plus 120 degrees, which is 120 degrees. So when I substitute it into the positive sine function, I have a new equation. Y equals to 2 sine brackets 3 times x minus 120 degrees, close out the brackets, plus 1. If I take the negative sine function and move it one cycle to the right, then I have 60 degrees plus 120 degrees for d, and so I have 180 degrees. If I use the cosine positive function and shift it one cycle to the right, then I have 30 degrees plus 120, and I have 150. Lastly, if I use the negative cosine function and shift it one cycle to the right, then I take negative 30 degrees, add 120 degrees, and then I have that 90, positive. I can also shift them one cycle to the left, and then I'll get different numbers. And then I'll substitute them back into the corresponding equations. I don't have to move them 1 or 2 cycles right or left. I can move them any cycles I want. Now, why is it true? Let's look at it graphically. For moving the sine positive function one cycle to the right. So look at the picture here. Instead of the original one that I used earlier, I'm using this cycle. So when I check, d is 120 degrees. For the negative sine function that is shifted one cycle to the right, d is 180 degrees. If I look at the positive cosine function that is shifted one unit to the right, now d is 150 degrees. We can see it clearly from the graph. And then if I use a negative cosine function, then you can see that it is a 90 degrees shift to the right. I can also shift them to the left. So this one is shifted one unit to the left of the positive sine function. So d is negative 120 degrees. For the negative of the sine function, we get d equals to negative 60 degrees. For the positive cosine function that is shifted one cycle to the left, now my d is negative 90 degrees. And then the last example, if I take the negative of the cosine function and shift it one cycle to the left, now my starting point is at negative 150 degrees. So, depends on how you want to look at one cycle of the curve, the equation that you end up with can vary.